All right, let's jump right into this explainer. Today, we're tackling something genuinely fascinating: how artificial intelligence actually sees and geolocates the physical world around us. Specifically, we're going to look at how convolutional neural networks, or CNNs, can predict map locations using literally nothing but raw visual data. So, I want you to take a quick look at this scene. How would you figure out where you are? I mean, if you've ever played GeoGuessr, you totally know the drill, right? You get dropped into a random street view somewhere on the planet, and you just have to pinpoint your location. The real question is, do you think you could beat a machine trained to do the exact same thing? It's the ultimate geolocation challenge. Take this random street view from Budapest, for example. As a human, you'd probably scan the image looking for, I don't know, architectural styles, specific kinds of trees, or maybe squint to read a street sign way off in the distance. But a machine, it takes a completely different approach to analyzing this exact same space.
Section 1. The Geolocation Challenge.
You can really see the contrast here between how we operate and how the AI operates. We rely heavily on semantic clues. We read signs, we recognize languages, we spot a specific car brand. But CNNs, they're operating on a fundamentally different, almost mathematical level. They extract pixel patterns, they detect high and low-level edges, and they use self-attention mechanisms. And if you're not familiar, self-attention basically helps the AI understand how completely different parts of an image relate to each other. It captures hidden dependencies that our human eyes would just, well, completely ignore.
Section 2. Enter convolutional neural networks.
It's kind of wild how fast AI geoguessing has evolved. Back in 2015, which feels like ages ago in tech time, Stanford researchers built early CNNs like Little Planet just to predict originating cities. Fast forward to 2020, and methods got a lot more sophisticated with grid-based spatial tile prediction. And then bam, 2023 hits, and the landscape completely shifts. We get vision transformers and clip models, which are just light years better at capturing complex long-range context across a whole image.
A perfect example is the modern street clip pipeline. It uses contrastive language-image pre-training. Basically, it associates images with the most relevant text labels, like the name of a specific country or city, in a shared mathematical space, so it can make zero-shot predictions just by directly matching visual embeddings with text. Pretty clever, right?
Section 3. Grids, cities, and coordinates.
Now, how does it actually map the world? It uses spatial indices. Think of it like throwing a giant invisible mesh over the Earth's surface, subdividing it into distinct geographical cells. By doing this, the AI isn't just taking wild guesses at random mathematical coordinates. It actually frames geolocation as a classification problem. It's basically looking at an image and saying, okay, which specific predefined bucket on the map does this belong in?
And you can brilliantly see this grid approach in action here. You've got researchers literally mapping out tiles over Portugal, and then this really cool heat map over a 10 by 10 grid of Budapest showing exactly where the training data is concentrated. By using these grids, the model learns to firmly associate specific visual features with a very confined spatial zone.
Section 4. What the AI actually sees.
Okay, this is where it gets really interesting. A research team at Brown University fed an image of Budapest into their CNN, and the model nailed it. It correctly predicted the location right near the actual center of the city. On paper, absolute success. But the real shock is exactly how the AI came to that conclusion. They used a line explainer, which is essentially a tool that highlights exactly which pixels the neural network is obsessing over. The dark blue areas show the heaviest weights. And guess what? The AI completely ignored the buildings. No way, right? Instead, it based its highly accurate prediction almost entirely on a random dark blotch in the clouds and the bumper of a parked car in the corner. Absolutely wild. So as the researchers pointed out, these algorithms are basically memorizing microscopic textures. They're using weird patterns in the sky, camera artifacts, or the literal texture of the dirt on the road as their primary clues, rather than actually recognizing the city's infrastructure. It's getting the right answer, but using a completely alien logic. It's literally staring at dirt instead of a beautiful cathedral. Let's quickly look at the numbers, because the drop-off is fascinating. City-level categorical accuracy. Incredible. It's sitting at about 90.2%. But asking it to predict the exact grid square drops the accuracy to 74%. And predicting the exact latitude and longitude remains mathematically noisy. It just goes to show the model really struggles when you ask it for pinpoint coordinate precision.
Section 5. Limitations and dataset biases.
Now, obviously, this tech isn't flawless. Because these CNNs are trained mostly on Google Street View images, which, are taken from moving cars, they get incredibly confused if there's no visible road in the photo. They also inherit massive object detection blind spots from base models like ImageNet. They constantly fail on rural images because the data is so heavily clustered in major cities. And, my favorite quirk, when they simply don't know the answer, they have a habit of just defaulting to the geographic center of their dataset.
You can actually see that statistical clustering in action right here. Notice this completely erroneous prediction pinned right in the dead center of Budapest, even though the real location is way further out. Why does it do that? Well, because that's where the vast majority of its training photos were concentrated. It's essentially just playing the statistical odds.
Section 6. The Future of Geo-Reasoning. Okay, so where is this all heading? We're actually witnessing a massive transition away from standard classification, those black box models that just guess regions based on road dirt and cloud textures. Instead, we're moving toward what's called geo-reasoning. This uses large vision language models that actually analyze explicit semantic clues, finally bridging that gap between human logic and machine processing. These newer models are trained so differently. Get this, they literally integrate human knowledge scraped from expert gamer communities like GeoGuessr. So now the AI can explicitly reason, hey, this image is in Chile because it actually identifies textual clues like a regional style of terracotta roof. They use vision transformers to capture the global context of the whole scene, not just isolated pixels, and they even generate a locatability metric to figure out how visually distinct a given spot actually is. As these models start blending this superhuman pixel analysis with actual real-world semantic reasoning, it leaves us with some pretty profound questions. If an AI can pinpoint exactly where you are from a random blurry photo of a tree or a brick wall in the background, what does the future of digital privacy even look like in our increasingly mapped world? It is an absolutely incredible technological leap, but for sure, it gives us something deep to think about the next time we casually post a photo online. Thanks for hanging out with me for this explainer, and remember to keep questioning the world around you.